Today we are going to take up calculus of residues. Question number 1. What is the residue of f of z is equal to z plus 1 by z minus 1 whole cube at its singularity? Z is equal to 1 is the singularity. In this case, it's a pole of order 3. We can see it here. So the residue is 1 by 2 factorial limit z minus 1 whole cube into the function z plus 1 whole cube by z minus 1 whole cube. But we must differentiate this 2 times d square by dz squared as z tends to 1. So this will get cancelled. We differentiate this function 2 times. So 1 by 2 factorial limit as z tends to 1. First time it is 3 times z plus 1 whole squared. Second time it is 6 times z plus 1. So when you apply the limit, you will get 12 by 2 factorial, which is 6. Therefore, the correct option is B. So the idea is, when you have a pole of order n plus 1, the residue is calculated as 1 by n factorial, limit at that singularity, nth derivative of the singularity to the power of n into the function. In this case, n is 3, therefore you differentiate 2 times and don't forget to divide by 2 factorial. So this is the fastest way of calculating the residue at a pole. We all know that singularities can be of 3 types. They can be poles, they can be essential singularities, or they can be removable singularities. So one must be able to decide whether the singularity is a pole or the remaining 2 types of singularities. If it is a pole, you are in an advantageous position. Otherwise, you will have to go for the power series expansion, and the Lorentz series will tell us about the entire residue story. Let's go to the next question. Question number 2. What is the nature of the singularity and the residue of the function f of z is equal to z minus 3 into sine 1 by z plus 2? Now you can observe that we have got a singularity at z is equal to minus 2, but the nature of that can be guessed. The function sine of 1 by z plus 2 has an infinite power series. So therefore, we can say that the singularity will be an essential singularity. So let me first expand sine of 1 by z plus 2. All of us know sine theta can be expanded as theta minus theta cube by 3 factorial plus theta power 5 by 5 factorial and so on. Accordingly, let's expand the function given to us. F of z is equal to z minus 3 into theta is 1 by z plus 2. So 1 by z plus 2 minus 1 by 3 factorial 1 by z plus 2 whole cube and so on. So if you can actually take z plus 2 in, we get this, and residue, as all of you know, is the coefficient of 1 by z minus a or 1 by z plus a. So definitely the second term is of no interest to us. So it is the first term which holds the key. So therefore, let's break this as z plus 2 minus 5 by z plus 2 and other terms. By doing so, we can extract the coefficient of 1 by z plus 2. So you can see that the residue is equal to minus 5. In fact, we should also try to see whether anything is possible in the second term, but even if it is done, you will not be able to get the 1 by z plus 2 term at all. So therefore, z plus 2 by z plus 2 will give us 1, and minus 5 by z plus 2 would be the real term that we require, because that's the coefficient, that is the term which contains a negative power of z plus 2. So you can see that residue is minus 5. So the result is z is equal to minus 2 is an essential singularity. This is the first question that we have to answer. Number 2, the residue is minus 5. But that happens to be the coefficient of 1 by z plus 2. So this is how you must handle an essential singularity, and it comes through the power series expansion. Let's go to the next question. Question number 3. From here we will be entering the application of the residue theorem. What is the output of contour integral 4 minus 3z by z into z minus 1 into z minus 2, where C is the circle mod z is equal to 3 by 2. You can see very clearly from the function that we have got 3 poles, z is equal to 1, z is equal to 0 and z is equal to 2. Poles are located at z is equal to 0, 1 and 2. All poles are simple. Perhaps you know simple poles carry power 1. Now if you look at the contour given to us, mod z is equal to 3 by 2, it is a circle of radius 3 by 2 with center at the origin. Now the poles z is equal to 1, z is equal to 0 lie within the contour. But if you take z is equal to 2, it goes outside the contour, which means we are interested only in 2 residue calculations, residue at 0 and residue at 1. So let's calculate R1, which is residue of f of z at z is equal to 0. And we know the residue formula for simple poles, limit z tends to 0, z minus 0 into 4 minus 3z by z into z minus 1 into z minus 2. Right? In the second case, when we take the pole at z is equal to 1, we get z minus 1 here. Okay, that we will see. You cancel off this and just put z is equal to 0 in whatever remains. So you will have 4 minus 0 by minus 1 into minus 2. So therefore this will give us 4 by 2, which is equal to 2. So that is how we calculate the residue at 0. In a similar way, we can calculate residue of f of z at z is equal to 1. Repeat the process, limit z minus 1 into the given function 4 minus 3z by z into z minus 1 into z minus 2. So now you make the cancellation again and then substitute z is equal to 1. So you get 4 minus 3 by 1 into minus 1. So that makes it minus 1. In that way, we have both the residues calculated. As I told you, z is equal to 2 lies outside the contour, therefore we don't require any residue calculation. Now comes the evaluation of the integral. So I is equal to 2 pi I into R1 plus R2. This is how the residue formula is applied. 2 pi I times R1 plus R2. R1 plus R2 is 2 minus 1, which is 1. Therefore, it is 2 pi I into 2 minus 1, which is 2 pi I. And therefore, you can see that the correct option for this problem is B. Now, matters will become a little bit difficult when we don't have simple poles. When you have poles of order 2, order 3, the differentiation has to take place. And then, of course, the residue theorem is very simple to apply. Let's go to the next question. Question number 4. What is the output of the contour integral e power minus 1 by z sine 1 by z dz, where the contour is mod z is equal to 1. So, the contour is a unit circle. And now we will have to analyze the singularities. Now, you can see that e power minus 1 by z and sine 1 by z, both of them have infinite expansions. Therefore, z is equal to 0 will be an essential singularity. However, in order to get the residue, we will have to expand in the Lorentz series. So, let us look at the Lorentz expansion. E power minus 1 by z into sine 1 by z is equal to 1 minus 1 by z plus 1 by 2 factorial z squared and so on. This is the expansion of e power minus 1 by z, to which we should multiply the sine 1 by z expansion. So, which is 1 by z minus 1 by 3 factorial z cube and so on. Now, once you have this, you just have to multiply appropriate terms and only be concerned about the 1 by z coefficient. Now, let us see how we get that. This produces a 1 by z term, and then if you look at every other combination, you get 1 by z. 1 by z is not possible in other ways. 1 by z cube, 1 by z square, those possibilities arise, in which we are not interested. So, because this is the only combination which produces the 1 by z, therefore, the residue is equal to coefficient of 1 by z in the Lorentz expansion. And this happens to be 1. So, the residue is calculated, z is equal to 0 is a singularity, and now we can write the answer to the integral. So, the value of the integral is 2 pi I into the residue, which is 2 pi I into 1, which is 2 pi I. So, at the end, it is a very simple problem, provided you know the Lorentz expansion of all the fundamental functions. The correct option, as you can see, is B. Question number 5. What is the output of the contour integral sine pi z squared plus cos pi z squared by z minus 1 whole squared into z minus 2, where C is the contour, mod z is equal to 3. Now, let us analyze this question. You can see we have got poles. Z is equal to 1 is a double pole and z is equal to 2 is a simple pole, and the contour is mod z is equal to 3. Now, let us look at the location of the poles with respect to the contour. Z is equal to 1 obviously is here. Z is equal to 2 also lies inside. So, therefore, we will have to do the residue calculations both at z is equal to 1 and z is equal to 2. So, let us calculate R1. Residue of f of z at z is equal to 1. This will be 1 by 1 factorial limit 1 derivative of z minus 1 whole squared into the function as z tends to 1. This was discussed in an earlier example also. So, now when f of z is substituted, the z minus 1 whole square will get cancelled, leaving behind limit d by dz of sine pi z squared plus cos pi z squared by z minus 2. So, you will have to differentiate this once and then substitute z is equal to 1. So, let us do the differentiation. So, you will get limit z minus 2 into, this will become cos pi z squared into 2 pi z. So, 2 pi z cos pi z squared minus 2 pi z sin pi z squared minus of 1 into sin pi z squared plus cos pi z squared divided by z minus 2 whole squared. This is the u by v differentiation, as you can see. Now, you do not have to bother simplifying this, but you can directly substitute z is equal to 1. So, when z is equal to 1 is substituted, let us see what is the result. Now, this will be cos pi, this will be sin pi. So, sin pi is 0, this sin pi is also 0. So, what remains is only this and that. So, when you put z is equal to 1, you get minus 1 into 2 pi into cos pi is minus 1, this is closed, not required, minus of again cos pi is minus 1 divided by 1 minus 2 whole square is 1. So, you will have 2 pi plus 1. So, this is the residue at z is equal to 1, and mind you, it has come not easily, but through process of differentiation. But the next calculation z is equal to 2 is a simple pole, therefore, we can get that a little bit quickly. R2 is equal to residue of f of z at z is equal to 2 by formula is limit z minus 2 into f of z as z tends to 2. So, when f of z is substituted here, z minus 2 will get cancelled and you will be left with limit z tends to 2 sin pi z squared plus cos pi z squared by z minus 1 whole squared. So, straight substitution, when z is equal to 2, this becomes sin 4 pi, but sin n pi is always 0, therefore, this becomes 0, but this becomes cos 4 pi is 1 by 2 minus 1 whole squared. So, this is going to be just 1. Sin 4 pi is 0, cos 4 pi is 1, 2 minus 1 whole square is also 1. So, therefore, you now have both the residues with you and we can write the output of the result. So, let me wind up. I is equal to 2 pi I into R1 plus R2. So, this will be 2 pi I into 2 pi plus 1 plus 1. So, this will be 2 pi plus 2. You can take a 2 outside and you will have 4 pi I into pi plus 1. And you can see the correct option for this problem is A. So, please observe that there are two residue calculations. One was a little bit lengthy because of double pole and one was a simple pole, but the residue theorem calculates much faster than the Cauchy's integral formula that we have learned long time back. Question number 6. Now, we are now trying to take up 3 examples which are related to evaluation of real integrals, but using the contour integral technique. So, question number 6. What is the output of integral 0 to 2 pi d theta by phi plus 4 cos theta? For all functions integrals of this type, the sin theta cos theta type, the contour is mod z is equal to 1. Now, mod z is equal to 1 implies z is equal to e power I theta and the parameter range is 0 to 2 pi. So, now you can Perhaps remember cos theta is e power I theta plus e power minus I theta by 2, and which when converted in terms of the complex variable z will give you z square plus 1 by 2z. This can be remembered directly. Of course, there is no sin theta, but in case there is a sin theta, we all know the conversion will be e power I theta minus e power minus I theta by 2i, giving z square minus 1 by 2iz. Right now we are interested in this. And apart from this, z is equal to e power I theta will give us d theta is equal to dz by iz. That is easy to visualize because dz is equal to I e power I theta d theta, where I theta is again z. So therefore, d theta is equal to dz by iz. So now this integral will be transformed as what? Integral over c dz by iz by 5 plus 4 into z square plus 1 by 2z, using this cos theta and using that d theta. And therefore, when you simplify this, you get 1 by I contour integral dz by 2z squared plus 5z plus 2. Now you can easily see that this can be factorized. However, in these types of problems, it may not always be possible that you may factor into real factors. Sometimes complex factorization may be required. This is a much easier case. So when you factorize this, you will get dz by z plus 2 into 2z plus 1. Now you can easily see we have got two poles, z is equal to minus 2 and z is equal to minus half, and the contour is mod z is equal to 1. So when you look at that contour, z is equal to minus half is here. It's on the real axis. But z is equal to minus 2, which is the other pole, is outside the contour, for which residue is not required to be calculated. So let us calculate residue at z is equal to minus half. So this will be limit z tends to minus half, z plus half into the function. So once you have that, f of z, as you can see, is 1 by z plus 2 into 2z plus 1. Therefore, when you make this as 2z plus 1 by 2, the 2z plus 1 will get cancelled, and you will have limit after the cancellation 1 by 2z plus 1. 2z plus 1 is gone, so you will have z plus 2 and obviously into 2. This 2 is because we are taking LCM here, as z tends to minus half. So when you substitute that, what will you get? 1 by minus half plus 2 is 3 by 2 into 2. So you will get 1 by 3. So 1 by 3 is the residue. As I told you, the residue at z is equal to minus 2 not required because minus 2 happens to be outside the contour. So let us write the value of the integral now. So the value of the integral will be 2 pi I into residue. So this is 2 pi I into 1 by 3. This is 2 pi I by 3. But let us not forget that there is already a 1 by I outside, so that we must not forget to include in the calculations. So I will get cancelled and we will get 2 pi by 3, and you can see the correct option is A. So please remember one thing, that these are all real integrals, and obviously the output should also be real. There must be no presence of I anywhere. If you can ensure that, you are on the right path. Dx by x square plus 9 into x square plus 4 whole squared. Now this is another real integral. and the contour for such integrals is an infinite semicircle r tending to infinity. Now, a lot of theory goes into it, but basically when you convert this into a contour integral, it is minus r to r f of z dz plus integral over gamma f of z dz is equal to integral over c f of z dz. So, the contour C consists of the real axis from minus r to plus r and then the integration over gamma. So, the integration on the real axis, you do not have to write z, it is enough to write x. Now, the theory says that this integration over gamma will vanish. So, this will become 0 under certain conditions. Okay? That is when you make r very, very large, then that integral vanishes. So, what is left is integral minus infinity to infinity f of x dx is equal to integral over c f of z dz. And in this case, the function is, I think better we write that also, f of z is equal to 1 by z square plus 9 into z square plus 4 whole square. So, the evaluation of this real integral, amounts to evaluation of the contour integral on the right hand side. So, you can see that there are two poles here, z is equal to 3i and z is equal to 2i. 2i is a double pole. So, therefore, there are two residue calculations in this problem. The first residue calculation at 3i, the next at 2i. So, let us do the calculation. R1 is equal to residue of the function at z is equal to 3i. So, this will be limit z minus 3i. The function, as I told you, is 1 by factorize z square plus 9 as z minus 3i into z plus 3i and write this z square plus 4 whole square as it is, because that has got nothing to do with this pole at z is equal to 3i. So, when these two things gets cancelled, what do we get? This becomes 6i. So, 1 by 6i into z square becomes 9i square. 9i square is minus 9. Minus 9 plus 4 is minus 5. Minus 5 whole square is 25. So, this becomes 1 by 150i. That is what we get. This is about the residue at z is equal to 3i. Similarly, what we do is, you calculate the residue at 2i. Now, you have to be careful because it is a double pole. Apply your formulas correctly. Limit d by dz 1 by, now you do not break z square plus 9, but you break this one. So, z plus 2i whole square into z minus 2i whole square. This is a slightly long calculation, but I am sure here we forgot one thing. We forgot to write z minus 2i whole square. So, this will get cancelled with this, and then whatever remains 1 by z square plus 9 into z plus 2i whole square should be differentiated, and then you apply z is equal to 2i. You will get certain result. Now, when it comes to the value of the integral, what is that you are going to get? Minus infinity to plus infinity 1 by x square plus 9 into x square plus 4 whole squared becomes 2 pi I into r1 plus r2. r1 I have calculated, r2 you please do that, and then you will get some pi by 100. Please verify. But what is required is 0 to infinity integral. Therefore, the minus infinity to infinity becomes 0 to infinity if this answer is divided by 2. So, therefore, we can say integral 0 to infinity dx by x square plus 9 into x square plus 4 whole square is equal to half of pi by 100. So, this becomes pi by 200. So, we will find D is the correct option. So, the student is expected to do this calculation, but he knows how to do it. One differentiation and then you apply the limit and then the problem is solved. These problems normally consume time. So, they may be the slightly longer types of problems that may appear in big exams. Question number 8. To evaluate the real integral minus infinity to plus infinity cos mx by k square plus x squared. So, this is the third type of real integral that I am explaining, and these integrals are called Fourier integrals. Fourier integrals are very critical in some certain types of frequency analysis problems. Now, the contour even for this problem will be the same that we discussed last time. The only requirement in this case is cos mx or sin mx should not be directly handled, but they must be converted in terms of exponentials. Now, all of you know that cos mx plus I sin mx can be compactly written as e power I mx. So, therefore, when you look at the problem given to you, cos mx happens to be the real part of e power I mx. So, we can write this as real part of integral over c e power I m z by z square plus k squared dz. So, the contour being the big semicircular contour, and then we don't, as I told you, directly use cos mx or sin mx, but put it in terms of exponentials. Now, you can see that z is equal to plus or minus ik are simple poles, but it's only z is equal to ik that lies inside the contour. Z is equal to minus ik goes below the contour. Therefore, we don't have a residue calculation for that. Now, we are trying to calculate the residue at the pole z is equal to ik. So, residue at z is equal to ik is equal to limit z tends to ik z minus ik into e power I m z by z minus ik into z plus ik. Now, you can get this cancelled and then put z is equal to ik, and you will get e power I m into ik divided by 2 ik. I square is minus 1, therefore, we will get e power minus km by 2 ik. This is the residue. The other residue is not required. So, you can write the value of the integral now, integral minus infinity infinity e power I m x by x square plus k square dx is equal to 2 pi I into the residue e power minus km by 2 ik. So, I will get cancelled, 2 will get cancelled, and you will have pi by k e power minus km. But let us not forget that this consists of two Fourier integrals, the cos as well as sin. But our problem is a cos integral. Therefore, you must take only the real part of the output. So, if you can add to this 0I, then actually we are attacking two problems. We are attacking the cosine problem as well as the sine problem. Let us see both the results. So, minus infinity infinity, expand e power I mx, you will get cos mx plus I sin mx by x square plus k square dx is equal to the right hand side, pi by k e power minus km plus 0I. Since we are interested in the cosine integral, the real part will be the answer. So, therefore, the answer will be pi by k e power minus km, which corresponds to the option D. Fourier integrals are very similar to the previous ones, but the only extra precaution we have to take is never directly take cos or sine, but put them in the exponential form. Do the evaluation as before, but break the answer into the real imaginary parts. If you are doing a sine integral, equate the imaginary parts. If you are doing a cosine integral, equate the real parts. So, this lecture should help students to understand how to calculate residues, how to identify singularities and their nature, and then how to use the Cauchy's residue theorem to evaluate complex integrals, as well as using the same theorem for real integrals.